ever wondered how stars form? Get ready to satisfy your curiosity. Stars are formed from dense clouds of interstellar medium. These molecular clouds, or nebula in the Milky Way, usually contain about 70% hydrogen, 28% helium, and 2% other heavier gases. But how do these nebula actually form stars? A cloud of dust and gases like this is not very likely to collapse and form a star on its own, unless acted upon by an outside force, such as an exploding supernova, or the interaction of two molecular clouds. Once this stimulation occurs, gravity pushing into the cloud begins to overcome the pressure pushing out, and the cloud shrinks. The smaller it becomes, the more gravitational attraction there is. Since the equation for gravity divides by distance, having a smaller distance between particles will result in more gravity. As the nebula collapses, it heats up, because the gravitational potential energy of the particles is converted to kinetic energy as they move towards the center. It also begins to rotate faster due to the shrinking radius. As the clumps of gas collide during the collapse, the particles merge into a flat, dense clump that will eventually become the star. However, before a star can form, the collapse has to stop. This happens as pressure slowly increases to equal gravity. Thermal pressure depends on temperature and density. As both of these values increase, the pressure grows to equal gravity and prevents further internal collapse. Once the star is hot enough, it begins to use hydrogen fusion. When the nebula is powered by hydrogen fusion and no longer gravitational collapse, it can officially be called a star. Nuclear fusion is the combining of two or more atoms into a bigger atom, and it releases 3 to 4 times the energy released by nuclear fission, the force behind atomic bombs. There are many different types of stars. They vary in shape, temperature, and color. We usually think of red stars as being the hottest, because we associate red with fire, which is obviously hot. But think of the blue fire produced by a gas stove. This is much hotter than typical candle flame light. In the same way, blue stars are the hottest. They are so hot that they produce high-frequency light waves, which are seen to the human eye as blue. Blue stars are also typically bigger, although red giants and supergiants can rival them in size, but not density. Hertzsprung-Russell diagrams are used to graph the surface temperature versus brightness of a star. The graph uses absolute magnitude, which can effectively compare brightness by assuming that all the stars are in the same distance from Earth. In reality, a star's apparent magnitude is determined by distance, which makes a closer, smaller star seem brighter than a large, far-away star. The Hertzsprung-Russell eliminates this distance and compares stars equally. A star can have multiple places on this graph during its life, due to its dynamic life cycle. 90% of stars are in the main sequence, powered by nuclear fusion and not changing much. However, when a star gets near the end of its life, it begins to run out of hydrogen for nuclear fusion. This is how red giants form, because the nuclear reactions move towards the shell of the star, where hydrogen is still present. This expanding atmosphere can engulf nearby planets. When this happens to our sun in 5 trillion years, the Earth will be destroyed by these fiery hot reactions. The expanding atmosphere of a red giant continues to fuse hydrogen, but the core of the star collapses due to gravity, much like the collapse of a nebula to originally form a star. This collapsed core becomes extremely hot and dense, and can start nuclear fusion again, but this time powered by helium. However, the helium supply will not last as long as the previous hydrogen supply. When it runs out, the star will enter its final stages of death, and they vary based on the star size. Regular stars give off pulses of hot gas called planetary nebula. Red giants become unstable and eject stellar material around the core. Once all the material is dissipated into space, it can collect a new nebula and be used to form future stars. All that is left is the core, which is a glowing white-hot ball called a white dwarf. Although small, these stars are incredibly dense. Most are smaller than Earth, yet way more than the Sun. One spoonful of matter from a white dwarf weighs several tons. Slowly over time, they lose their thermal energy. And since they're no longer doing nuclear fusion, they fade out into cold black dwarfs. Larger stars experience a more dramatic death. When they run out of nuclear fuel, there is no pressure to overcome the force of gravity pulling inward. The star collapses to the core and then violently explodes outward in a massive explosion known as a supernova. Star matter catapulted away at speeds of 30,000 kilometers per second can eventually be reused to make more stars. Similar to the death of regular stars, all that remains is a core. One type of core that can come from this is a neutron star, which is compressed so much that the atoms are split apart and only neutrons remain. This type of star is so dense that one house full of its matter would weigh as much as the moon. However, black holes, the other resulting cellular body produced by the death of a giant star, are even denser. Not even light can escape their intense gravitational pull, and they can swallow planets, stars, and even other black holes. We don't know much about them since we can't see inside, but we do know that it's best to stay away. Hopefully this has helped satisfy your curiosity on stars and their life cycle. I'll see you next time when Curiosity Calls.